Okay, we're here today. We're going to spend most of our time just answering any questions that you have concerning the course or the final examination. Okay, so I'm a terrible actor. Okay, any questions then that you have about the examination at all? How you doing on the examination? Did you get everything you think?
I feel better today than yesterday, but still struggling with some things.
Okay. Do you want to elaborate at all, or what would you like to do?
One of the things that I think you mentioned in a class that we were going to speak about that, but yeah, I had this question: how the power spectral density relates with the autocorrelation.
Okay. Well, the power spectral density is nothing more than the Fourier transform of the autocorrelation. So that's the incredible part about it. But in order to have a power spectral density, you must have a system which is at least wide sense stationary. So if you do that, you have a power spectral density. So I don't know. I mean, that's it. They're Fourier transform pairs. And I tell you something, that's something that I've been kind of wrestling with ever since I saw this. I'm not sure how the power spectral density relates to the autocorrelation, because the autocorrelation is one thing, the power spectral density is something else. And
I'm sorry.
and so the power spectral density measures the power in the frequency domain, and the I'm recording here. Okay, yeah, go away. Thank you. And the power. I'm sorry. Did you enjoy that? I hope you enjoyed that as much as I. Get out of here. What's that?
It was excellent.
Thank you. Thank you.
I was like, there's somebody moving around in the background. And I was like, oh man, Dr. Mark's like, must be his brother or something.
It was my evil twin brother. That's right. He bothers me all the time.
I didn't even know you could do that with Zoom. No, it's hilarious.
Oh yeah. Well, okay, we're deviating a little bit, but there is a way where you can put your own background in, including your own videos. For example, let's see, video settings. For example, I made this background a while back, which I'm very proud of. Where to go? I guess it's this one with the exploding kernels. And so you can have a video and then you can upload the video into Zoom and have it as the background. So that's where I got that. Okay, let me get rid of that. Okay, as far as the relationship between the autocorrelation and the power spectral density and why it works that way, I don't know. I just don't have an intuitive grasp why the power spectral density is related to the autocorrelation. So I don't know if that helps or not. I wish I could give you some intuitive insight, but unfortunately I can't.
I wish it will help to make clear that if my if my answer is correct or not. So I will double check later. I need some time to know.
Okay. Yeah. So you'll have to figure that out, I suppose. Yep.
Yes.
Yeah, okay. I had a question.
Sure.
On the first problem, I think it's the first problem. We have the signal that's band limited, and then we're adding in white noise.
Yes, for the sampling theorem. Yes.
Yes. I just want to make sure that I'm correct in thinking about this. When we sample the white noise, because we are summing over an infinite n,
yes,
we can perfectly recreate the white noise.
No.
No.
The sampling theorem only works for band limited signals.
Oh.
And the white noise has a spectrum which is constant forever and ever and ever.
Yes.
So,
So even if you have
therefore, yeah, go ahead.
Okay. Even if you have an infinite summation, you still can't perfectly recreate.
No, you're not reconstructing the original noise. It's almost like sampling a signal that is no longer band limited. However, the information that I gave you is sufficient for generating the autocorrelation. And I'll give you a hint. It's kind of like passing it through a low pass filter in a way.
Okay. Okay, thank you.
And you should get a point in that problem where you had the sink convolved with the sink. Did anybody get that? Did anybody get that far? No? Okay.
I was stuck on the same point with the sampling theorem and the white noise.
Okay. Did you get an integral over a product of a couple of sinks? Anybody get that far? Okay, wow. Well, here's a little bit of a hint. You get the summation of an autocorrelation function, and then it's a double sum. I think you probably all got to hear it's a double sum over the autocorrelation times there's an integral in there. The double sum of an integral, let's see, no, there's no integral. There's a double sum over the autocorrelation times a sink, right? Did anybody get to that point?
I did not. I think I got messed up on the sampling theorem and took a different path, and it ended up being kind of so easy that I was questioning.
Oh, it's so easy. Yeah. Were you reconstructing the noise in your assumption?
Yes.
Yes. No, you can't do that. You can't do that. Shame on you. No, yeah, that's okay. That's okay. White noise has a spectrum which goes on forever and ever and ever. And as we said, it kind of doesn't exist. So let me try something. And hopefully get you to a point here of understanding. Before we do that, I need to ask you a question. I want to ask you a question. And that is, if you can see my screen now, hopefully. Okay. Did anybody get A?
I did something, but it's so simple that
It is. It's incredibly simple.
okay, then it may be correct.
Okay. Anybody get what the autocorrelation and mean of Q of T is? Q of T is a stochastic process corresponding to the noise. Did anybody get this far?
I think I did.
Okay. And what did you do there? What'd you get for the autocorrelation? Tell me your final equation. What does it look like?
Okay. It's a constant times a delta function.
Okay. No, I don't think that's true. No, because you're assuming here, I think that you're reconstructing the original noise, which you're not. Okay, with that, let me try to give you a head start at this. Well, where'd you go? Oh, there you are. Okay. Okay, let's see. Yep. Okay, my incredible thing is working. So you have, this is the original sampling theorem. If you look at it, it's very beautiful in a way. The summation over n means from minus infinity to infinity. It's x of n over 2b. times the async of 2bt minus n. Let me tell you why that's so beautiful. It's so beautiful because if you have a number of samples here in a signal, and you would like to regain the original signal from the samples, you take each sample and you weight it by a sinc function. So this sample here gets weighted by a sinc function. Now the sinc function is 1 at the origin. So when it's weighted by the sinc function, it comes down like this. And it goes through 0 for all of the other signals. That's really cool. It goes through 0 for all of the other signals. Or all the other samples, I should say. Where's the colors? There we go. Okay. In a similar fashion, the sinc for this one goes through all the zeros of its adjacent samples. And this one goes through the zeros of all its adjacent samples. And then what happens when you get done, you add up all of these and you get some sort of signal, which I'm doing in the purple here. But here is the cool part. You're assured that the purple signal passes through these samples. Why? Because what's the contribution here? The contribution here is the value of the sample here plus 0 contribution from this sample plus 0 contribution from this sample plus 0 contribution from all of the samples. So you know when you add up all of the sinks that the sinks are going to add up to be whatever that value is. And that's kind of a beautiful, I think it's a very nice result. So that's kind of the sampling theorem. Okay, let's go back to what we're talking about here. And then we have, what do we call it, Z of t? I forget what the result was. What was X plus the noise?
It's Y.
Okay.
And then you sampled Y to get Z.
Right, okay. So that is Z of t, and Z of t is not equal to Y of t because Y of t is no longer band limited. Since this has an X of n over 2b plus, what did I call it?
E.
E, thank you. So we're all agreed with this. Now, did everybody get that first term that this was equal to X of t plus Q of t? That's the one that's really simple, right? But Q of t is just equal to the summation of the noise it's just equal to the summation of the noise interpolated by the sinc. Now, in order to get the correlation function of Q, we won't assume at this point it's wide sense stationary, even though it is. Anybody get this far?
I guess I was stopping myself. I thought that there had to be some further simplification on Q there, but I got there.
Yeah, no, I don't think, well, you got there, but then did you just plug and chug? This is equal to the expected value of the summation over n. And then Q of tau, we have to be careful here. We can't use the same n here. N is a dummy variable, right? So therefore, we have to sum over some other variable. Let's call it m. To be tau minus m. Okay? So if we shuffle these together, we get the summation of n over m, and I'm just going to isolate the stochastic part, which is the e's. Anybody get this far? Does this all make sense so far? What is this recognized as? That's recognized as the autocorrelation of the noise, correct? Except it's not evaluated specifically at time. It's evaluated at n and m. But since we've given that this is wide sense stationary, this is the same thing as n minus m over 2b. See, normally we would say this is r sub e of n over 2b, m over 2b, right? That's the normal definition of this autocorrelation function. But since we know that it's wide sense stationary, it's the difference between the two. And I guess there should be a 2 here. Is that okay? Okay, the answer should be yes. Okay, so we're therefore good up to this point. And then notice this is a one-dimensional function. Yet we have summation over 2 dimensions. So let's get rid of one of the variables and set k is equal to n minus m. And we're going to make the variable substitution for the m sum. In other words, we're going to treat n as in nunchucks. We're going to treat the n as a constant and make this variable substitution. This will make this into an r sub c of k, r sub e of k, right? Do you agree with that? And we will be left with something like the summation over k of r sub e of k over 2b. I should have put a k over 2b here. Times the summation over n of some sinks. I'm not going to fill in the sinks. I don't want to work it for you. Is that okay? Now, this will turn out to be a discrete time convolution. You can look at it that way, as I mentioned, and it should give you another sink. Here's another way to look at it. You can look at it one way if, 2bt minus n, and this other thing is going to be stuff. But you can look at it as this part as the summation over n of, say, some function w. There's 2 ways to look at it. Number 1 is to evaluate this as a discrete convolution. The other way is to look at it with the sinc part equal to a W, and you'll notice this is the sampling theorem. The sinc is already band limited, right? The sinc is band limited. And so this turns out to be then W of T. And the beauty of it is it lets you get rid of the summation over N, which is going to be the same no matter what your signals are. So yeah, hopefully this will give you a summation of over K of R sub E, K over 2B. Times some sort of sinc here. Well, and R sub E, this is white noise, right? So R sub E, what is that equal to?
N naught over 2 times the delta function.
Yeah, N over 2 times the delta function. So you should be able to play around with that and simplify this sum. So I'm not going to work it all for you, but I think that this is sufficient enough. And somebody said they got a delta function. Was that Theo or?
Yes.
Okay, so you well, this is not good because what is R sub E at 0? R sub C at 0 is equal to, what's it equal to?
Is it like the power spectral density?
No, it's equal to infinity, right?
Yeah.
So anyway, I hope you can play around with that and come up with some sort of semblance of an answer. I've worked it out for you almost, but not quite totally. Ooh, look at that screen. Looks like a bunch of chicken scratch, doesn't it? Okay, so with that, I'm going to stop sharing my screen and ask if there's any other questions. Hopefully that'll get you a running start towards that problem.
Thank you. Yeah, I see the mistake I made. So thank you.
Okay. Since you guys haven't got very far, let me change the problem. Okay. I'm going to change this problem, but I'm going to do it offline, okay? So take a look at this. I'm going to make it so it's a little bit easier for you. I saw in working the problem where I can make it a little bit easier. I guess you're not seeing my screen, but I'm going to make the power spectral density a little bit easier for you, okay? So I will change that immediately after class and yeah, hopefully make it easier and more transparent. Any other questions about the exam? Did you get the first problem okay?
I had a question on number 2.
Okay, question on number 2. Let me get that up here.
Specifically on part E.
Oh, E, okay, yes. Let me go ahead and share my screen here. Okay, part 2, yes. Which one? Part E?
Yeah, E. So is the process mean ergodic? One question I kind of had is when you say is the process, are you talking about Y of T or X of T?
What's the average power? Both. Let's just do X of T. I'll make it simpler for you. That's probably a good question. Okay.
Okay, yeah. And then I guess my second question, I may have to, I was thinking it was y of t, so my second question was kind of based off that it was y of t. So I guess I'll have to go back and look and see what changes with x of t, because I was thinking you need to know the autocorrelation, which you don't exactly have.
Well, let's see.
But for x
Look,
of
we
t,
do-
you're given.
Yeah, we do. We do have the autocorrelation of x of t. It's up here, right?
Now we just need to find the, like there's one more step that you have to do, and then you can compute it.
Yeah, if you have the autocorrelation, which is given up here, if you have the autocorrelation, which is given up here, that's enough to determine whether you have mean ergodicity.
Okay, yeah.
Okay.
Yeah, that main thing I was wanting to kind of clarify what you were asking on part E.
Okay. Okie doke. I do want to share one more step, which might help you in doing this this exam. There we go again. Let's get rid of all of that. We know that x of t has a Fourier transform, x of f, which is 0 for f greater than some bandwidth b. Is that okay? That's the definition of band limited that we are using. And when this is the case, we have the sampling theorem. And the sampling theorem gives you the x of t. Right? So with this in mind, suppose that we had this summation. Can anybody tell me what this is equal to?
That should be equal to 1.
Yeah, it should be equal to 1. It's just like all of these samples here are equal to 1. Now, is x of t a band limited signal? Well, x of t is equal to 1 as a Fourier transform of what? A delta function? And the question is this equal to 0 for f greater than b? In other words, we have this delta function sitting here, and then we have minus b to b, and this x of f here. Is this equal to 0 for this interval here? Yeah, sure it is, right? So a constant is a band limited signal. So if you come up with something like this, you can evaluate this as equal to 1. And it kind of makes sense graphically too, because if you have a bunch of 1s here, these are your samples, and you do that sync sort of thing. It kind of makes sense that it might end up adding to 1. You know, at least the interpolation goes through 1 because of those beautiful properties of the sync function. So yeah, it does add up to 1. So this summation is always equal to 1. So that will help. Okay. Any other questions at all?
Regarding the part B of the exercise 2, using a 2-ohm resistor, if I may ask this, is like using a 1 ohm but multiplying the result at the end by 2.
Well, you have to know the equation for power.
Okay.
And there's an old phrase that beginning electrical engineers know, which is twinkle, twinkle, little star, power equals I squared R. Okay.
Okay, power equals
I squared.
I square?
Yeah, the current squared.
I square R. Okay, so, okay, perfect. So that makes, yeah, if that's what it is, I guess that product gets to the end of the result. And
Yes.
okay, thank you.
You're basically computing I squared and then you pop in the R at the end. So
Okay.
we did that for context.
I thought it was too simple to be true.
It is simple. It is simple. But the entire idea there is getting you to look more at, how should I say it, more in terms of the context of application. I didn't want you to always assume that the average power was equal to the expected value of the stochastic process squared. That's not, it's only equal to that when you are doing things on a 1 ohm basis. Okay.
Okay.
Okay. Any other questions at all? Okay, seeing as everybody was having difficulty with that one problem of the sampling theorem, I'm going to change it from continuous white noise to discrete white noise. That is, each sample is perturbed by zero mean discrete white noise. And I think that should maybe make the problem simpler for you, okay? And you'll avoid the direct deltas and the infinities and things of that sort. Any questions at all?
I have one
Theo.
question remaining. If we talked about a process being mean ergodic,
Yes.
we say that the mean doesn't change over. We can take a sufficiently long sample of a process.
Yes, and the question is, can we do the mean over a long process? And our counterexample of a stationary process where you couldn't do that was the battery factory, if you remember.
Mm-hmm.
You can't take just a single realization of one single battery and figure out the mean of the entire population of batteries.
Right.
But there are other processes where you would assume that it would be mean ergodic, and you can look at one realization and you can determine in the limit the mean of the process.
Mm-hmm. Okay, thank you. Yes.
Okay. So yeah, we have to assume already that the mean is a constant, since our theory was only applied to wide-sense stationary stochastic processes. We did not consider mean ergodicity for any other sort of problem.
I see.
Okay.
Okay, thank you.
Okay, anything else? Okay, so I'm going to make the problem a little bit simpler, hopefully, and hopefully the hints I've given you will give you the wherewithal to make it through. If you hit any bumps that are unanswerable, drop me an email and maybe we can hash it out that way. Okay. Okay. Thanks, everybody. It was a fun semester for me, even though I have been remote from you. I don't think I've ever met. Let's see. I don't think I've ever met Matthew, Theo, or Justin. Have we met in person?
The only time I've ever seen you in person was when you came into Dr. Loomis' class to like watch him and stuff, and you were just sitting in the room.
Oh, I sat in the back. Yeah. Okay.
That was the only time I've seen you in person.
Okay. Well, I'm better looking in person, just so that you know. Okay. Okay, gentle people. Notice my use of politically correct descriptors here. Gentle people, it was a great time. We'll see you in a bit. I will be putting this on YouTube if you want to take a look. Bye-bye.
Thank you.
Thank you, Dr. Marks.